Now we're up at chapter 13.2. Observations of different types of dust, gas, stars, and star clusters reveal the shape of our galaxy. So last section we learned that we knew there was a center and we knew we weren't in the center based off of those variable stars. Those variable stars in the little star clusters, they pointed us towards the center. And we had to use those because we couldn't see through the dust of our galaxy. Well, if we look at the dust, we look at the gas, and we look at the characteristics of our actual disk, that helps us determine the shape. One of the things that we've been carrying with us for probably since like chapter 2 is the fact that light travels a little differently than maybe we thought of originally. Specifically, different wavelengths of light can do different things. In this case, infrared light passes more easily through dust and gas than the higher energy forms of light. Which means if we build detectors and telescopes to look for infrared light, we can see things that we cannot see with visible light telescopes and with like X-rays and stuff like that. Because this type of light can pass through the dust, we can see through the dust. What we find is that most of the dust in our galaxy lies in the plane of the galaxy, like this. All right? And what we see here is the far infrared light. What that means is it's the farthest away from our visible light that can be detected. This is measured using just barely infrared light, which means this is a lot closer to being able to actually see it with our eyes than this is. And you'll notice there's a slight different shape. Here we can clearly see there's a central bulge and then it kind of tapers out over here. But here, it's kind of even. I would say it's a little more like spread out on the edges. But you can tell that they look similar, but they're not exactly the same. Okay? So this is showing us where the dust is coming from. And this is showing us, honestly, where mostly stars are giving off light. And we see that even though there's a lot of stars here, there's about the same amount of dust everywhere. So this is why it's useful to look at these different wavelengths of light, because we get different amount of information. We're looking at the same things here in both of these pictures, the exact same thing. But we're getting different results because one of them is looking at the far infrared, and we're looking at this, which is the closest to visible light infrared, the near infrared. But it's the same picture. So, if an astronomer wanted to study the nature of cool stars hiding inside dust clouds, which wavelength would be the best choice, near infrared or far infrared? Well, near infrared wavelengths can pass through dust. So if we wanted to ever see anything through dust, we'd still probably want to use that near infrared. Okay? Mostly because the dust itself is giving off that far infrared. But like in this picture, these stars are giving off the near infrared. So either this is through the dust, this is the dust. So it's better to use the near infrared because that can go through the dust as opposed to actually looking at the dust. Putting this on a couple math and theorems and stuff that we're not going to go into altogether, we realize that the stars in our galaxy are evenly distributed across the disk. And that disk is about 160,000 light years in diameter and about 2,000 light years thick. The center of our galaxy is surrounded by a tightly packed distribution of stars called the central bulge, which is about 6,500 light years in diameter. And then there's a couple other stars that are kind of running around doing their own thing around the central bulge and around the disk. These spherical distribution of globular clusters trace the halo of our galaxy. And again, here is an artist's representation of what a galaxy looks like because we have never seen outside of our galaxy like this. We have the central bulge right here. We have the entire disk like this. And then these stars are the halo stars that kind of make this a circle. There's obviously not nearly as many halo stars as there are stars in the disk. here's what our galaxy probably looks like. These are what other galaxies look like, but based off of the characteristics of ours and what these look like, we can say ours are probably similar to what this looks like. This is actually the same galaxy. I'm sorry, I should have read the caption. Same galaxy, but it's at different wavelengths. Different wavelengths of light. Still infrared. Both of them are infrared, but different types of infrared. But this is what our galaxy probably resembles. So let's say you're in a spaceship and you want to look at the sun. Would it be better for you to be inside of the galaxy and looking at our star? Inside the galactic center of our galaxy? Or would it be better to go and maybe be near one of those halo stars? Well, hopefully you guys realize if we were in the center of our galaxy, you could not see through all the dust to see our star. It'd be much better for you to be on one of the halo stars so you can look essentially down onto the disk and look down onto our star with a lot less dust to look through. But if you're in the galaxy with us, you have to look through all that dust. This is what I mean by the halo stars aren't really part. So we're like in this disk, right? Most of the stuff's in the disk or in the bulge. But these stars are way like going around really far. So it's a lot easier to see from here, from here down than it is to see from here over because of all the dust in the way. Something interesting we know about the halo stars is that they're composed of old, isolated, metal-poor population 2 stars, which means they're probably some of the first ones that our galaxy had, which means there's a low rate of star formation. There's not a lot of new bright blue stars out there. It's all old red ones, essentially. All the young stars in our galaxy are usually in the disk. So the stars in the disk are mostly young, metal-rich population 1 stars, like the sun, indicating active star formation. Now, I should have been a little more specific with my vocabulary. I said the blue stars. That's not the case. Just most of the stars in the disk are young, metal-rich population 1, meaning they weren't the first generation of stars. That means that the globular clusters aren't really making new stars, but the disk is making new stars. If we look towards the center of our galaxy, the central bulge has both population 1 and 2 stars, but is primarily dominated by older red giants and supergiants. That actually kind of gives us the idea that the central bulge also isn't really making any new stars. It's mostly old red giants and red supergiants, not a lot of new stars. And not a lot of bright new stars, especially, not like blue ones. Okay, so breaking down this picture, both population 1 metal-rich and population 2 metal-poor stars are found in the central bulge, but no young blue stars exist here, meaning no active star formation in the central bulge. Only population 1 stars are found in the thin galactic disk. The presence of hot blue young O and B stars indicate active star formation is occurring, which means in the actual disk, like where we are, it's possible to get those really bright blue stars because the disk is still making new ones. And then all the way out here in the globular clusters, there's only very old population 2 stars there. So those stars are not, those clusters are not making any new stars. So the only place our galaxy is making new stars really is in the disk. So if you were looking to find the most recently formed stars in our galaxy, where would you look? Hopefully you know, because I just said it. It's in the disk. And that is it for section 13.2.